All right. Hello there to those of you watching the recording. We're going to jump into graph theory today. So the next 3 weeks are going to be all about graphs and how to use them well, I guess 2 weeks actually, 2 weeks, this week and next week. We'll talk about graphs, how to use them, how to draw them, the different ways you can compute using one. And so I'd like to begin by just talking about the most basic idea of what a graph is. So a graph, G, is a pair of two sets where V is the set of vertices and E is the set of edges. Okay, cool. So an edge, well, maybe we should talk about what's a vertex and what's an edge before I get more formal here. Let's talk informally about what's a vertex and what's an edge, right? So if I have a graph like this, the dots are the vertices and the lines are edges, right? So I could label these guys, A, B, C, D, E, right? And so the vertex set in this case would be what? A through E, right? So I'll have A, B, C, D, and E. But what is the edge set like? Right? How do I represent the idea of a connection between A and B, but there's no connection between, say, A and D? Yeah, we could use a little set, right? So we could say, okay, well, A and B are connected, and so we'll put the set A, B into E. So E is actually a set of sets, right? So what other sets are going to go into E, the edge set? Okay, BC, CD, DE, and finally EA, right? Cool. Okay, so we have our vertex set, and then we have our edge set, and our edge set is a collection of sets of two vertices, right? Now, there's another kind of graph called a directed graph where there's a direction associated with each edge, right? So, for example, if I had this situation, okay? Okay, now you can see there's a direction associated with each edge because there's a little arrow, right? So what would my vertex set be in this case? Good, A, B, C, D, right? But now that I do my edge set, there's a little bit of a problem. What's the problem? Sets aren't ordered, right? And we need an order to say which vertex or node, another word for a vertex is a node, right? I guess I should say nodes, plural. We have to say which node we're coming from and which node we're going to, right? So what mathematical structure has an order to it? Like I said, I want to use that instead of a set. So Nathan, yeah, so an ordered pair is what I'm looking for. So I wouldn't call, I guess I would call this the head and this the tail. But that terminology is not really used in a directed graph. That's more for vectors. But in a directed graph, these things aren't supposed to be vectors. They don't really exist in a coordinate plane. Like these A, B, C, and D, these don't have coordinates to them or anything like that. They're just sort of, it's an abstract list of connections between things. And those things don't have any particular location. So it's different from vectors in that way. And the head tail terminology, I personally haven't seen that used to talk about graphs. So does that make sense, Nathan? Yep. Okay. If we were to use it, I would say, just as in vectors, A for this top arrow, A would be the tail and B would be the head. But I haven't seen that terminology. So if we want to do some ordered pairs here, okay, so we've got from A to B, right? That's that top arrow I was talking about, right? And what other pairs do we have here? Okay, AC, CB. Okay, so AC, CB, BD, and CD. Yep, that's perfect. BD and CD. Okay, so if you have a directed graph, then you would want to use a set of pairs for your edges. With an undirected graph, it's this guy, undirected, you would be using a set of sets for your edges. Okay. Well, let me show you something interesting, right? What if I was to take this graph and draw it in a different way, okay? So what if I take this first graph, this pentagon here, and instead I draw this, right? Well, something interesting is going on here. There's a relationship between these two graphs. Can anyone tell me what it is? They're the same. Okay, well, how could we label the vertices in this graph so that the edge set is identical to the edge set from our pentagon, right? So let me get you started. Let's say the top of the star is A, right? What would I need to label next in order to sort of make this graph have the exact same edge set as this one? Yeah, the bottom right would be B, right? Because A connects to B, right? So as we go forward, right, we can go B. We could have gone the other direction too, but down this way is fine. So we have A connected to B. Okay. And then we can see that B is connected to C. So what would we have to put in next? Yeah, the top left is C. Excellent. Okay. And then? Okay, the top right is D, which I guess that leaves the bottom left to be E, right? And if you go through and create the edge set here, you'll be able to see it's exactly the same as the one before. We have AB, right? A connects to B, B connects to C, C connects to D, D connects to E, and finally E connects to A. And of course, the vertex set is, A, B, C, D, E, like above. So what does this tell you about graphs? What have you learned here? There's more than one way to draw it, right? And I think that should be pretty clear if I was to do something like this, right? Here's one representation of the graph. Here's another one. And I think you'd feel pretty comfortable in saying that these two graphs are the same, right? I mean, this one's stretched out long, but it's the same things are connected to each other, right? And so long as the same things are connected to each other, it's the same graph no matter how you draw it, right? Now this one's quite a bit wackier than this one. Here we've actually pulled vertices down over some of the other lines and sort of mixed everything up, right? But I mean, you could imagine, well, I take I take B and stretch it down here. I take D and stretch it up there. C goes over there and E comes down. And if I was to move all those vertices around while keeping the connections intact, maybe these are like rubber bands or something, so they can stretch and move around, but I can move these points around on the plane and make a star shape. And it really is essentially the same graph. When I say essentially, that's not the technical term. Does anyone know the technical term for the relationship between these two graphs? Isomorphic, very good. You know what isomorphic means? It's from the Greek.
ISO means the same, morphic means shape.
Yeah, good. Yeah, shape or form. Yeah, that's right. So it means the same shape or the same form. And I think form is a little bit better in this particular case because obviously they're not the same shape, right? But they're the same, they have the same pattern of connections between the vertices in both graphs, even though they're drawn differently. So yeah, isomorphic is the word we want here. That's great. Right? Because if you morph something, you're like changing the form of it, right? So the form is morph. Iso means the same. Like an isosceles triangle has two legs that are the same length. So iso means same, and morph means shape or form. Great. Okay. So isomorphic graphs are kind of interesting, right? Because as you can see, maybe you're surprised that these two are the same, and you should be. That's pretty weird that a star and a pentagon are actually, have the same underlying pattern of connections between them. So, maybe from that you could guess that there are graphs that are isomorphic to each other. When you look at it, it's not clear at all that they're the same, right? You'd have to actually go through and find out who's connected to who, right, before you could see if they're actually the same graph or not. And so there's a little nifty problem to start with. Any questions about that? Or how about this? Can someone give me another pair of isomorphic graphs? Any thoughts there? No, no ideas. Here, why don't I give? Well, okay, so a coffee mug being a donut is not about graphs. That's about topology. So isomorphisms exist in a lot of different parts of mathematics. And so Lucas, you're talking about a topological isomorphism versus a graph isomorphism. If you converted it into a mesh, well, then unfortunately, that mesh is going to possibly be different depending on how you converted it. And so, think about if you wanted to have a 3D, sort of matrixy looking, by which I mean a wireframe coffee mug, okay? And I think you'd be able to see there are lots of different sort of wireframe coffee mugs we could make that would all look like a coffee mug, but they would have different wires connected to each other in the wireframe, right? So yeah, so I think in that case, really what you're getting at is that the surface of a coffee mug is the same as the surface of a donut if you stretch out the figure of the coffee mug into a donut. So you know what? I would bet there's going to be a nifty video of that online. Let's see if I can find it, because it really is a similar idea, but it's not exactly the same. So let's say coffee mug isomorphic. Boy, it's just not going to do isomorphic for me. Oh, there it is. Okay, great. Oh, here, this is great. Oh, this is a ceramicist. Mathematicians like to do art, so that's always fun. So you can see here, right, the coffee mug sort of morphing and stretching into a donut shape. And what makes something topologically isomorphic is the number and arrangement of holes in the surface. And this coffee cup just has one hole where the handle is. Same with the donut. So these are the same topologically because they have the same number and arrangement of holes, which is a little bit different than a graph isomorphism, right? With a graph isomorphism, it's that everyone is connected to everyone else in the same pattern, right? So can someone think of a different graph isomorphism rather than a topological one? Oh, and sorry, David had one. A triangle and a square, one line is two edges. I'm not quite sure what you're going for there, David. Oh, you mean like a house? You mean like a house shape? Like a first grader drawing a house? Is that what you're talking about? That? Is that the graph you're talking about there, David? No, square to triangle. The triangle has two edges in one line segment. Do you want to draw a little picture and show us? So I'm still, or you want to try English one more time? It's hard to talk about graphs without drawing them, right? In the meantime, I can certainly do something to this to make it another one that's isomorphic but looks pretty different. Here's that same graph, right? A house is the same as an envelope, the same idea. All I did is take the top point and pulled it down there, right? So there's an example. So David, you want to try your example one more time?
Yeah, I was just saying that a square, if you just bring, say, the upper left point.
Okay, we have a square. We take the upper left point, yeah.
And bring it onto the diagonal between the upper right point and lower left point.
Okay, I see what you're saying. You're talking about this, is that right?
Yeah.
Yep, absolutely. These two are isomorphic as well. Yep, very nice. So there's quite a few examples. Sometimes things are isomorphic that are not easy to see. So maybe I should, let me show you one of those and then we'll move on and do some more vocabulary here. So let's look for a graph isomorphism. Okay, so there's a star in the pentagon. Okay, here's a couple examples here. These guys. This is this is called the Peterson graph. That's a pretty weird isomorphism there. That's a pentagon, that's a hexagon. It's got all this crazy stuff going on inside. So that one might be kind of surprising, right? Here's another way of looking at the cube graph. So there's a cube, and it turns out you can put them all into two groups there. we're going to talk about this arrangement of a graph is called a bipartite graph because there's two parts, so it's bipartite. So there's a few different examples of graph isomorphism. Here's another example of the Peterson graph. Right. So there we go. Oh, we had a chat question here. Wait, let me stop sharing. Okay, cool. We didn't have a thing. Okay, great. So, so let's do some more vocabulary, right? Because in order to really dive deep into graphs and the way that they work, what we're going to need to do is talk about the properties of graphs, and then sort of investigate how those properties work over a variety of examples. So I'm going to give you some properties, and then we're going to talk about how they work and find some equations that can describe them in some different situations. So, all right. So a simple graph has no loops or parallel edges. Okay. So let's do some examples of non-simple graphs, right? So here's a non-simple graph. That is a loop. It's an edge that goes from a vertex back to that same vertex. That's a loop, right? So an edge from one vertex to the same one. What do you think parallel edges are? What do you think that means? Lines go in both directions. Kind of. They don't have to be directed to be parallel. They could be undirected and parallel. So can you generalize that a little bit, David? Two edges connecting the same two vertices, right? So for example, these would be parallel edges, right? And if I want these to still be isomorphic, I'll pop another one onto there, right? Okay, so parallel edges are multiple edges that connect the same two vertices. A loop is an edge that connects a vertex to itself, right? And a simple graph doesn't have any of that crazy nonsense, right? We're going to be able to prove some things about simple graphs, and that proof wouldn't work if we had some of this weird loops or parallel edge stuff, right? So that's why we're talking about simple graphs. We'll be able to prove some stuff about them. Okay. So let's do a complete graph. What do you think a complete graph is? Close. It's not that all vertices have one edge. It's a little bit more than that. There's a way to get from the starting point, touch every point, and get back to it. That's a Hamiltonian circuit. So that is a thing, but it's a different thing. Okay? So Seth, you were on the right track. It's not that all vertices have at least one edge. Rather, it's that every vertex is connected to every other vertex. That's exactly right, Sean. Yeah, very nice. So a complete graph has an edge between every pair of points, pair of vertices. Let's start calling them verts for short, right? And you can actually number these according to how many vertices they have. Because if you And put it this way, there are different ways of drawing the same complete graph that are isomorphic to each other, but really there's only one complete graph that has, well, let's do some examples. There's only one complete graph that has 3 vertices. What is it? Where am I going to draw in edges here? A triangle. Good. Right? Every vertex connects to every other. Okay, so let's go up. This one is called K3, by the way. It's called K because the Germans and Austrians and Prussians back in the day developed a lot of graph theory, and complete is spelled with a K in German, right? So that's why we have K3 instead of, C3 or something like that. K2 is just a line. Yep. So here, let me pop K2 in here. Here's K2. Right? K1 is meaningless because it doesn't have any edges. Right? Let's try K4. Okay, so what am I missing here? Got A, B, C, and D. Yeah, the X, the diagonals in the middle. A, D, and B, C need to go in. Very good. Okay, what about K5? A star goes in the middle. Very nice. Okay, there's K5. How about K6? So I'll have a hexagon here. And here it starts to get a little bit intense, right? So let's put in all the edges, A, B, C, D, E, F. So what am I missing? Okay, we want an X. Oh, and a line across. Okay, so we've got a line across and an X. Okay, is that everything? EC. Okay, yeah, we need EC. Good. What else? EA. Yep. CA. Sure. BD. Yep. Couple more. FB. Yep. And lastly, FD. Very good. How do we know that we're done? I mean, it looks kind of symmetric. It looks kind of cute, I guess. Does that mean we're done? If it looks cute? Is there a better way of telling? Can count degree. Okay, what's degree? The degree of a vertex is how many edges connect to it. How many edges is, maybe I should say the number of, that's better terminology. The number of edges adjacent to it. Okay. So what's the degree of this vertex? Two. How about this vertex, B, on the pentagon, or on K5, I should say? 4, right? And this vertex A here on K4? Yeah, it's 3 because each vertex in a complete graph is n-1, right? So you can tell that because these are all simple graphs, right? So nothing connects to itself. And so, for example, for A, there are only 3 other vertices that you connect to. And of course, you have to connect to all of them because it's between every pair of vertices, right? And so you can see A has 3 edges coming out, one to B, one to D, one to C, one to each of the other vertices in the graph. So how would we be able to tell if our graph K6 was correct and complete? What would the degree of each vertex have to be? 5, right? Okay, so let's look. For A, we've got 1, 2, 3, 4, 5. B, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, I think we got it, right? Yes, a vertex connecting to itself does mean something. It's called a loop, and it depends on what your graph is trying to represent, whether loops are appropriate or not. So, you know, if I'm trying to make a graph that describes, you know, who I'm friends with on Facebook, right? In that case, it wouldn't make sense to have loops because you can't be your own friend on Facebook, as far as I know. Isn't that right? I mean, that'd be pretty weird, right? Is everybody happy with that? So can someone give me an example of a system you'd like to use a graph to represent that does have loops in it for relations, its reflexivity? Yeah, yeah. So if you wanted to use a graph to depict those arrow diagrams we were talking about before, right? Then that would be a directed graph like this one, right? Because there's arrows in our arrow diagram. And it might be that if you have a reflexive relation, that you have an arrow pointing from A to itself, which would be a loop, right? So yeah, so I think using an arrow diagram as a graph would be a great example of why you might want to have loops in there. Yeah. I don't think that one would have parallel edges though, right? Because you know, if something relates to something else, you just draw one arrow. You would never draw like 2 arrows that go from one thing to the other because you only need one to represent it, right? So a relation arrow diagram would have loops, but it would not have parallel edges, right? And so, you know, you can think of, you know, something else that maybe does have parallel edges. What if you wanted to represent, you know, like a road map, okay? And the vertices here are cities and the edges are the roads or maybe freeways that connect them, right? And so, you know, if there's 2 roads to get from one city to another, then maybe you would want to represent that by 2 different edges that connect them. So maybe there's an example of a graph that uses parallel edges for representation. Does that make sense? Cool. All right. So let's talk just a little bit more about these complete graphs. There's another way that I could figure out if I finished out the graph correctly or not. And to do that, I'd like to make a little table. So if I have the number of vertices here and the number of edges here for a complete graph, I have K2, K3, K4, K5, and K6, right? Well, of course, this will have 2, 3, 4, 5, and 6 vertices, respectively. How many edges are they going to have? Well, we can sort of fill it in. What do we start with? This, by the way, is the size of the vertex set and the size of the edge set. These are like absolute values, right? So what's the size of the edge set of K2? 1. How about K3? More than 2. 3. Yep, 3. How about K4? Six. Okay, good. 1, 2, 3, 4, and then the 2 diagonals, 5 and 6. Okay, how about K5? Got a pentagon and a star, which each have 5 edges, right? So what's the total? 10. And then K6? 18. Not 18. That's a little high. That's okay. Yep, guessing a pattern is great. There's a nice pattern here we're going to talk about in just a second. 15. Yeah, cool. Okay. So do you see a pattern in this table? Can we come out with a formula for this thing? Yeah, it's the sum of 1 plus 2 plus 3 plus 4. That'll give you 10. 1 plus 2 plus 3 plus 4 plus 5. That'll give you 15. There's a name for these numbers. These are called the triangle numbers, because if I was to start making triangles, well, that's not a very good triangle, but here's a little bit better one. 1, 3, 6, 10, 15, right? So these are the triangle numbers, right? Which just means you add up everything up till and including the number in question, right? So given that, what would be the number of edges in Kn? So the number of edges in Kn is what? Maybe let's write it as a summation first. This is the sum from what? The sum from 1 to n, I equals 1 to n, of
N minus 1?
Or should it be n minus 1? Ah, yes, because for 6, we're only going up to 5. Yeah, very nice. So this will be n minus 1. Nice work. Okay, of what? Not n, because n's our total. What's our counting variable? Yeah, I. There we go. Nice. Of I. And we actually know a closed form solution for this. Yeah, I. You had the right idea. I is the counting variable, n's the constant, right? And what's the closed form for this thing? Yeah, good. N times n minus 1 over 2. As we've learned quite a few times now, right? This is Gauss's formula, right? N choose 2, right? Yeah, thinking about it in choose notation is kind of nice. Why would you be thinking about it in choose notation, Luan? Can you or someone else sort of interpret why n choose 2 relates to a complete graph? It's about somewhere in the book, sure. Yeah, well, it's definitely the same formula, right? I mean, we learned that last week, right? So there must be some relationship there between a complete graph and n choose 2.
Is
First
it
of all,
about like
go
how
ahead.
many ways you can pick 2 vertices out of n vertices to make all the edges?
Yeah, right, because all that each edge is a pair of vertices, right? So what this is saying is out of n things, how many different ways can you pick 2 of them? Well, if you take all of them, all the different ways you can pick 2 things out of n of them, that's going to be the exact same number as the list of vertices that need to be connected to each other, right? Yeah, great. Yeah, Nathan, you got it in the chat too as well. Yeah, nice. Okay. So it's a nice little formula we get for the number of edges in a complete graph. And we're going to see lots of other little formulas popping out, which reflect back on some of the things we've done this term and last term as well. So let's do another one here. Okay, cool. A bipartite graph which is called KMN. So it's complete, but with, oh wait, no, that's not necessarily true. Sorry, I lied. You don't have to have this. I'm going to leave that off for a minute. We'll circle back to that. Is a simple graph that can be partitioned into two parts. I'll just say that can be split into two parts. Where two things happen, okay? There are no, well, let me just do it this way. Where, I'll just describe it in English, where there are no edges between vertices in the same part. Okay. So let's see if you can tell me which of the complete graphs we've drawn here are bipartite. Maybe let me give you one example first. So here's an example of a bipartite graph. Usually they're listed in columns. So here's a bipartite graph, right? So here's part number one. They look a little bit like our function diagrams from earlier, but it's just a graph, right? And so, you know, there can be edges that connect, you know, between parts, but there can't be any edges that go from one part back into that same part, right? So this guy here is an example of a bipartite graph. And Sean, you think that K2 is bipartite? Sure. Here's how you can partition K2. There's one part, there's the other. So that's pretty easy. Okay, and K3 you don't believe to be a bipartite, is that right? Because you said just K2. Yeah, so why is K3 not bipartite? Tripartite, sure. Well, you could split it into three parts like that, right? Sure, but bipartite?
For all of the others, if you tried to separate any of them out such that like you could make a group where they didn't connect, I mean, they would connect because that's the definition of the completeness, right?
Yeah, good. That's perfect, right? Every node needs to connect to every other node, right? So if I tried to split it into, and I can split it up in different ways. So let's say I take K4 and I split it up into 1 and 3. So one part has one vertex in it. The other part has all three of the remaining ones, right? Well, this part's okay. It only connects to things in the other part. But this part on the right is not okay because it has interconnections inside the part. Well, okay, I can't split it 1 and 3. What if I split it 2 and 2? Well, that almost works, right? Because I've got this situation going on, right? But then unfortunately, I still have these guys that connect inside the parts, right? This one and this one, which renders it impossible. Well, let me ask you another question. What if I just had the square graph like this, right? So let's call this A, B, C, and D. Is the square graph bipartite? What I'm asking is, can you draw an isomorphism of the square graph in such a way that the vertices on the left don't connect to each other and the vertices on the right don't. And there's your two parts. Very nice, Sean. So if we have A and D on one side, right, and B and C on the other, well, who connects to who? Let's draw out our isomorphic graph. Well, A connects to B, sure, and A connects to C. D connects to B and C. So the bow tie is actually the same graph as a square, but now it's arranged in a way that it's clearly bipartite. Yeah? What do you guys think? Yeah? Because you can connect across, but you can't connect inside the same part. Cool. Okay. What about, oh, I don't know. What about a hexagon, right? The hexagon graph. Let me get some new paper here. I'm running out of room. So let's do the hexagon graph here. Oh, there we go. Okay. So we've got this guy. A, B, C, D, E, F. Okay. Can I make that one bipartite? Yes. Okay. So what's going to go where? So what's going to go on the left side? Let's start with the left. A, C, E. Okay. So we've got on the left here, we've got A, C, E. I guess on the right, that leaves B, D, and F, right? Okay, and where are our connections going to go? Well, A connects to C. Oh, sorry, pardon me. A connects to B. B connects to C. C connects to D. D connects to E. E connects to F. And F goes back up to A. Right? So it kind of does this like zigzag business until the very end where we come circle back to the very first one, right? And these are called ring graphs, right? So this is a 6 vertex ring graph, okay? And so I think it should be clear at this point that some ring graphs can be shown to be bipartite, right? We've shown a ring graph with 4 vertices, which is just a square, and then a ring graph with 6 vertices, that seems to work. Is there a ring graph that cannot be shown to be bipartite? Yeah, a triangle, right? We saw that one earlier. We can't do a triangle because no matter how we arrange it, right, there's always going to be, you know, a connection on one of the sides. Okay, are there other ring graphs that cannot be bipartite? Yeah, the odds, right? Because if we had a fiver, look what happens, right? If we had a pentagon, I'll start with A, B, I have to go to the other side, right? Here's my division. Anytime I have an edge, I got to go across. So from A to B, okay, B to C, C to D, D to E, and then since I'm forced to go back to this other side, if I have an odd number of vertices, I'm now forced to be in the same part that I started in, so that when I connect back to the very first one, the A, it's going to be on the same side, and that'll ruin my bipartiteness, right? Okay, well, let me ask you this. We had, you know, this hexagon can be bipartite, but the triangle couldn't. We said the triangle could be tripartite. Do you think we could make the hexagon tripartite? So now let's make 3 parts, right? All right, so we've got, let's start with A up here. Okay, so can I divide up my hexagon into a tripartite graph? Okay, you want A and D together, B and E, and then C and F. Okay, so let's see who connects to who, right? So A goes to B, B goes to C, C goes to D, D goes to E, E goes to F, and F goes back to A. Yep, so it looks like it works. There are no connections inside the parts, right? So what would you say is the relationship between the number of parts that you can partition a graph into for a ring graph versus the number of vertices that it has? Anyone see the pattern? Yeah, the number of parts has to divide the number of vertices evenly, right? We can make this tripartite because 3 divides evenly into 6. So does 2. 2 also divides evenly into 6. If we wanted to, do something that, we divide up into 4 parts, and it's a ring graph. Okay, it's got to be. If there's other stuff going on in the graph, then all bets are off. But if we just have a ring graph here, then the number of vertices, is going to have to be divisible by the number 4 if we were trying to divide it up into 4 parts, etc. Right? Now we could try to prove something like that, right? But I think let's hold off on that a little bit longer, right? I just didn't want to talk about bipartite for a bit, but we'll hold off on the proofs for a bit. Let me talk about a complete bipartite graph. A complete bipartite graph KMN is a bipartite graph with every possible edge inserted. I'll say included. I'll say a bipartite graph with parts of size. Sorry, I forgot a part. Size M and N. So let's do an example, right? So if I wanted to do K3, 4, okay, I'm going to have 2 parts. Right? On the left, I'll put 3 vertices. On the right, I'll put 4 vertices. And by the way, they're called vertices, not vertexes. Vertexes is not a word, right? So vertices. And let me label these. So let's call this A, B, and C, and I'll call this 1, 2, 3, and 4, just to keep things easy. So who's A going to connect to for a complete bipartite graph, K3, 4? Everything on the right. Okay, so we got connects to 1 and 2 and 3 and 4. Great. What does B connect to? Good. The same thing. Each thing on the left connects to everything on the right. And so, how many edges? What is the size of the edge set of KMN? 12 in this case, in general, for m and n? Yeah, m times n. And m and n are just integers, so I don't have to take they're not meant to indicate sets. They're just numbers, right? So I can just say m times n without the absolute values. Nice. Okay. So that's pretty cool. You can find the number of edges that way. Let's see here. Okay, let's talk about a subgraph, and then I think we'll circle back to degree. Okay, so a graph G may have a subgraph H where the vertex set of graph H is contained in the vertex set of graph G. Remember, these are sets, right? The vertex set of H, the vertex set of G. The edge set of H is contained in the edge set of G. Oh, thank you. Sorry. And for the last part, we have to think about something that might go wrong, right? So what might go wrong if we have a subgraph? Yeah, there's an edge connecting to a vertex that doesn't exist. Good, right? Because what if I did this? I have my graph G. Here's my graph G. Square graph ABCD, right? And here's my subgraph H, looks like this. And if I do this, A connects to B and A connects to C, I'm good. This is part of the graph of H. A subgraph is a part of the graph, right? But what I can't have is this situation, right, without a D on there, right? Because maybe I include in the edge set for H, I include the edge BD, but I didn't include the vertex D, right? So the vertex set is contained, the edge set is contained, and for all edges in the edge set of H, the endpoints of E are contained in the vertex set of H. Does that make sense? This one's missing an endpoint, right? The endpoints of this would be B and D, right? But D is not included in the, in the vertex set here. So this would be a bad subgraph, not allowed, right? Is everybody happy with that? Okay, can someone give me another subgraph of G with a vertex set and an edge set? Oops, it's supposed to be a vertex set H. A with no edges, okay? The vertex set has A, the edge set of H is empty. Yep, that's a subgraph. How about a subgraph with 2 edges in it? Someone give me, or let's do 3 edges. Someone give me a subgraph with 3 edges in it. Let's start with the edge set. There are 4 choose 3 options here, right? So there are 4 choices for an edge set with 3 edges. Take your pick. What do you want to do? So one more time, I think I lost you guys. So I'm looking for a subgraph of G that has 3 edges in it. And I'm wondering what those 3 edges should be. Okay, AB, BD, and DC. Okay, sure. So AB, BC, sorry, BD, and CD. Okay, and in that case, you have to look at the endpoints in here to see what go in the vertex set. We have A and B and C and D, so we need all 4 in the vertex set there. Yeah. Is everyone happy with subgraphs? Any questions? Okay, so let's do this. The total degree of a graph is the sum of the degrees of all the vertices. So we're summing over the vertex set. So we're summing for all vertices in the vertex set. That's a little v is a vertex, big V is the vertex set, right? We're summing over all of those, the degree of little v, right? So let's do an example. What's the total degree of K34? So I'm going to try to walk you up to a duh moment, but I need your help. So let's start with an easier one. How about this guy, the hexagon? What's the total degree of this guy? So I'm asking what the total degree is. So the total degree is the sum of the degrees of all the vertices in the graph, right? So for example, this is my hexagon, and here's an isomorphic picture of it. What's the total degree of the hexagon? Or its isomorphism, which is going to be equal. Yeah, 12, right? So you can say 2, 4, 6, 8, 10, 12, right? 2 for each in this case. Okay, how about the total degree of K34? Yeah, so there's 3 times 4, because there's 4 coming out of each of these guys. And here there's 3 coming out of each of these, so this would be 4 times 3. So the total would be then 24, right? What's the relationship between the total degree of the graph? Well, you tell me. There's a pattern here about the total degree of a graph. It relates to something really straightforward about the a really simple property of the graph. Can you tell me what it is? Double the size of the edge set, right? Because here we had 6 vertices and the total degree was 12. Here we have, well, here we have, 12 edges and the total degree was 24. So it looks like the total degree here is equal to 2 times the size of the edge set. it appears, right? At least in the two examples we've done. Why would the total degree equal double the size of the edge set? There's actually a really easy, dumb reason why that is. Each edge has two endpoints, right? Each endpoint of an edge contributes 1 to the degree, right? So if I look at this edge right here, right? So let's look at this edge. Well, this edge has two endpoints, right? And this endpoint contributes 1 to the degree of b. This side of it contributes 1 to the degree of d, right? And if you put them all together, right, each edge connects to two endpoints, which means it contributes 2 to the total degree, right? And we are only discussing simple graphs, but that's actually even true for non-simple graphs. So for example, if I had, this situation, a little loop on there, right? So here's a non-simple graph. What's the total number of edges? 6, right? 1, 2, 3, 4, 5, and then the loop makes 6. And what's the total degree? Well, let's count. What's the degree of A? 3. B is also 3, right? How about C? 2. And how about D? 4, right? So we've got 1, 2, 3, 4 things coming in. This one, even though it's a loop, it counts as 2, right? Because we're connecting on one side of the loop and the other. So they both contribute to the degree, right? So we've got 3, 3, 2, and 4. That makes 12, which of course is 2 times 6, right? So even if you don't have simple graphs, the total degree rule still holds. Yeah. And the reason why is because even on a loop, you're still contributing 2 to the total number of edges, to the total degree, right? And same thing with this parallel line up here. Well, this line contributes 1 to each of A and B. This one also contributes 1 to each of A and B, right? So we can actually go even a little bit farther here. Okay, so we know that the total degree of the graph, no, David, it's just called a not non-simple. Yeah, I would just, yeah, there's no special term for that. Yeah, not that I know of anyway. Let me know if you run across one. So what do we know then? If the total degree is 2 times the number of edges, what do we know about that number, the total degree? If it's equal to 2 times the size of the edge set. That's kind of a dumb question. I'll just answer it myself. It's even. Yeah, perfect. Yes, that's right, David. It's even, right? It's 2 times something, so the total degree is even. Well, that actually has some interesting consequences for the types of graphs that are possible to build, right? Because what if I had my, let's do a degree list. Three, 3, 3, 3. Right? So what I'm saying is there's 4 vertices and each vertex has degree 3, right? So I would call this a degree list. I don't think your book uses that terminology, but we'll just use it in here. I think it's a good way of putting it, right? So we have 4 vertices. Each one has degree 3. What graph is this? K4, right? It's this guy, right? Each vertex has degree 3. Well, what if I had this degree list? Can I draw that? It's not going to be a complete graph at this point. I can. Okay, yeah, how's it going to look? So first of all, do I just have 4 vertices? Is that right? So I guess I'm still going to have my 4 vertices here. Let's call them A, B, C, and D. Okay, so let's say A has degree 1, B has 2, C has 3, and D has 4. We need a loop on one because something has degree 4. Okay, so you're saying D has to have a loop on it if D is the degree 4 one. Okay, that's fine. What else are we going to throw in here? We don't want to loop on A because A only has degree 1. And a loop is going to contribute 2 to the degree number, right? So it would be too much, I think, if we put a loop on A. Right, okay. You want to connect A to B as one of the edges, okay? Sure. And then A can't connect to anything else. Yep, because now A has 1. Now B has degree 2, so what's that going to look like? Okay, we want to connect B to C. Okay, sure. So now B has degree 2, A has degree 1. So A and B are done. And we have C and D remaining. And C is supposed to have 3 and D is supposed to have 4. It actually can still work. Well, we can't connect B and D because B is already out of degrees. We've used up all 2 of them. But yeah, we can use parallel lines from C to D like this. Right? So now A has 1, B has 2, C has 3, and D has 4. The parallel lines come to our rescue there, right? But let's draw another version. Yeah, there's many versions of this that we can draw that are not isomorphic, right? So Lucas, your idea was to have D has 2 loops and C has 1 loop. So let's do that. So C has 1 loop on it. There's C. D has 2 loops on it. There's D. And what's left? A to B and B to C. Yep, that works, right? 1, 2, 3, and 4. Yep, that works fine. Let's do another one. Let's try to minimize the number of loops and parallel edges. Can we get away with doing this without any loops or parallel edges? You don't think so? Okay, why not? Why do we have to have at least 1 loop or a set of parallel edges? There's something that forces us to do that. Not the odds, actually. That's not it. Yeah, it's the degree of D. Since D has degree 4, there's only 3 other things it can connect to. Even if we maxed out the connections for D, we'd only come out with a degree of 3, right? And so to get that degree 4, D has to connect either to something twice or to itself, right? So let's put a loop on D, but let's try to not use any other parallel edges or loops. Okay, so we're going to put a loop on D. And what else are we going to connect where to get degree 1, 2, and 3 on these guys? A to D, okay, sure. And what else? Okay, B to D. Well, we don't want C to D and B to D because then D would be 5 instead of 4. So which one should I pick? Should I connect B to D or C to D? A should go to C. Very nice. Here, we're not going to have enough stuff left for C because we need 3 of them for C, which means C needs to connect to everybody, right? But C can't connect to D anymore. Oh, well, I guess C could, but then B is going to be in trouble, right? So C actually could connect, but then we won't have enough room for B. So I think that if we redo here, let's try one more time. A, B, C, and D. Okay, so D is going to have that loop on it. And A connects to C. Okay. And C connects to B. C connects to D. B connects to D. And I think that's it, right? So now we have degree 1, 2, 3, and 4 with only one loop. Nice. So as you can see, there's a lot of, and a couple people put other ideas in. There's a lot of different ways that you can build a graph out of a degree list. A lot of different graphs, non-isomorphic graphs you can make from a degree list, right? But sometimes you can't make you can't make a graph out of a degree list. What if I did this? What if I did, let's do this one. 3, 3, 3, 3, 3. I claim that that's problematic. Why? Yeah, it has odd total degree, right? So that's nothing because it's not even total degree. Nice. In order to have an even total degree, what do we know about the vertices of odd degree inside the graph? So we need even total degree, but obviously we can have some vertices that are odd degree. What do we know about the number of vertices of odd degree if the total has to be even? There has to be an even number of vertices with odd degree. Perfect, right? This one has A and C, that's 2 vertices of odd degree. This one has 4 of them, 4 vertices of odd degree, that works fine. But this one has 5 vertices of odd degree. And an odd times an odd gives you an odd. So that's not going to work, right? So not only does the total degree have to be even, but also the number of vertices of odd degree also has to be even, right? And so if you're given a degree list that has an odd number of odd degrees in it, you know for a fact that that's impossible. That's not a real graph, right? At least not according to the rules that we've set up where every edge has 2 endpoints, right? Okay, what do you guys think? Questions so far? It's fun, right? I mean, this hopefully is a lot more entertaining and interesting than probability theory. Is that the opinion I usually hear? What do you guys think? Does that sound right? I have to agree. Oh, you like probability more? Yeah, okay. Well, there you go. You know, there's one in every crowd, right? All right, cool. So cool. So let's take a break here, and we'll take 10 minutes, and we'll come back and do some practice problems. So take a break, stretch your legs, get the blood flowing, and I'll see you in 10. All right. So I thought we'd do some practice problems here. So for each of graphs 8 and 9, we're going to find these 8 items for each graph. So let's start with graph 8. We'll do all of these guys. Or no, let's just go back and forth. That'll be more fun. So in graph 8, find all the edges that are incident on V1. So an edge being incident on a vertex means it's next to it. So what do you think? What are the edges that are incident to V1 in number 8? Perfect. 1, 2, and 3. All right, and how about V1 in number 9? Which edges are incident to that? Just 1 and 2. Great. Okay, so for the second one, find all vertices that are adjacent to V3. So here's a V3 there. So which vertices are adjacent to it? Okay, so yes, and V3. So V1 and V2 are obviously connected, right? Adjacent just means connected to, but V3 also connects to itself, so that is included. Nice. Okay, how about V3 down here? Which vertices is that V3 adjacent to? Good, V1 and V2 connects up here and here. Okay, let's find all edges that are adjacent to E1. So here's E1 up top. So which edges are adjacent to that? Okay, 2, 3, 8, and 9. Perfect. Yeah, very nice. Okay, and how about E3? That would be this one here. So which edges are adjacent to E3? Okay, so this will be, yeah, there we go. Okay, 2, 3, 4, 5, 6. Perfect. Okay, so now let's find all the loops. So what are the names of the edges which are loops in number 8? Oh, and I should say, Lucas, E3 is not adjacent to itself. That edge is not adjacent to itself. I should mention that. A vertex can be adjacent to itself, but an edge cannot. That's right. I think that's right. I'll have to go check the definition, but I'm pretty sure. Why don't we finish this up and then remind me, I'll go check. So what are the loops in number 8? Okay, 6 and 7. How about in number 9? 1 and 3. Perfect. Okay. So then let's find all the parallel edges. So which ones are those in number 8? Four, 5, 8, and 9. Good. And in number 9? 4 and 5. Perfect. Okay. How about the isolated vertices? We haven't talked about that, but I think you can probably figure it out. What are the isolated vertices in number 8? V6. Yeah, nice. And of course, V4 in number 9 right here. Okay, great. So an isolated vertex is one that has no edges, right? Okay, what's the degree of V3 in number 8? So there's V3. What's its degree? Five. Excellent. And V3 down here in number 9, that has degree what? 2. Perfect. Okay, so what's the total degree of graph number 8? Twenty. Perfect. 3, degree 3, 3, 4, 5, and 5, right? 3, 3, 4, 5, 5 makes 20. Okay, how about number 9? What do we got here? 12. Okay, we've got 2, 2 makes 4, another 4 makes 8, and then this one's got 1, 2, 3, 4, 5, 6. Oop, I think it's 14. I think you missed 2. Did I get it wrong? Or did you? I think you got it. I think it is 14, right? 2, 2, 4 makes 8, and then another 6 is 14. Okay, so let's go back and look and see if an edge can be adjacent to itself. Okay, so here's the little definition part. Okay. So an edge is said to connect its endpoints. 2 vertices that are connected by an edge are called adjacent. A vertex that is at the end point of a loop is said to be adjacent to itself. An edge is incident on its endpoints, and 2 edges incident on the same endpoint are called adjacent. So 2 edges, 2 different edges, it's assumed, right, that connect on the same endpoint are called adjacent. So an edge cannot be adjacent to itself because you have to have 2 different edges, apparently. And that's not super clear in the book, but I think, in general, if you had a loop, you would not say that edge is adjacent to itself, even though the vertex would be. Because, yeah, there's no real good reason why. Okay, cool. So let's do some more practice. All right, let's do that. Move these guys over, get rid of the answers so you can't see them. Okay, perfect. So in each of these, we're going to draw a graph with the specified properties or explain why no such graph exists. Get rid of my little pencil marks here. No guessing. Okay, so what do you think about that first one? Is that a graph or no? Number 17. Yes, it is a graph. Okay, Can you draw a picture of it? Maybe someone would like to share screen. Does anyone have a screen and comfortable enough in Paint or Photoshop or something to draw little pictures, or have a webcam and a pencil and paper? Because we're gonna get, you know, for the next couple weeks, we're gonna need to, you know, some of the answers are gonna just be pictures, right? So if we're gonna be able to discuss, you are gonna have to, well, you know, you don't have to participate, but if you'd like to participate in the discussion, you're gonna have to have sort of a way of showing pictures to everybody. So maybe, let me do an example. So here, let me stop the video for a minute. Every Windows machine that exists has Microsoft Paint, okay? So it's time you learned how to use it. It's super easy. Let me do that. And someone was trying to chat here. Chat window. Okay, that's just a yes, okay. Okay, so so what we're supposed to do is 1, 2, 3, 3, 5 with 5 vertices. So let's make our vertices first. We'll make those red. Why not? So there's, oops. When I want a circle here, so I want 1, 2, 3, 4, 5. Doesn't have to be pretty, right? And then I'll put in the edges with lines. So I want one vertex of degree 1. Okay, so here we go. There's our vertex of degree 1. Then we need a vertex of degree 2. So let's make this next one a vertex of degree 2, right? Then we need a vertex degrees of 3, 3, and 5. Okay, so if we want to make this one 3, who else can it connect to? Okay, so I want, yeah. So I'm trying to make this a 3. I'm trying to make this one a 3, right? So if I want this to be degree 3, it's already got 1 for the degree. So who else should I connect to? It can connect to 5 and 3. Okay, so maybe I should have labeled these, huh? Maybe that would help. Let's call these A, B, C, D, and E. Okay. So one more time, David, who do you want to connect to here? E and D. Okay, great. So I've got this guy and I've got this guy. Okay, so now A, B, and C are done. D is supposed to be another 3, and then E is supposed to be a 5. So how am I going to make this one into a 3 and this one into a 5? I got a couple of options now. You want 2 loops on E. Okay, so let's do, you know, there we go. There's one loop. There's another loop. Boom. So 2 loops on E, okay, and 1 loop on D. Cool, that'll do it, right? Or I could have put in another edge between E and D. And if I do that, now what do I have to do? In order to get D up to degree 3, yeah, I have to put another one between D and E. So let me just freehand this one's going to look terrible, but that's okay. Oop. Big size here. Okay. And then after that, what's the last remaining thing to do? Oh, I'm sorry, you said it already, David. And then 1 loop on E. Oop. There we go. Right. So that's another option. Okay. So what do you guys think? Does paint make sense, right? You can do text here. This is freehand. If you want to do shapes like circles or lines or squares or anything like that, those are here. Pick your colors here. Relatively straightforward. If you want to change things, you can select things in a box, like move it around. Any questions about paint, how it works? So everyone with a PC has this program. All you have to do is go to the Windows menu and just type it paint, and it'll come right up, right? Okay, so let's move on to the next one. All right, so number 18. A graph with 4 vertices, degrees 1, 2, 3, 3. Does that graph exist? No, good, it does not. Why not? The total degree must be even, and in this case, it is not, because 1 plus 2 plus 3 plus 3, well, that's 6, 8, 9 is the total, and the total can't be odd. Okay, how about number 19? Does that one exist? No, good. And why not? Yep, same reason. The total's odd. Okay, number 20, we did that one already. 1, 2, 3, 4. We already did a bunch of examples of that, so you can see that one's fine. How about a simple graph with 4 vertices of degree 1, 2, 3, and 4? Does that exist? Number 21. No. Okay, why not? You can't get a 4 with 4 vertices, right? This 4 is saying you have to connect to 4 different things. Simple is saying you can't connect to yourself, right? Or to anyone else twice, which leaves only 3 vertices you could connect to. So the maximum degree you can have in a simple graph is the number of vertices minus 1. And that rule is being broken here at number 21, right? Here, instead of n minus 1, we have n, which is too big. How about number 22? Simple graph, 5 vertices with that degree list. Nope, same reason. Very good. So this one says 5 vertices, but we have a degree of 5 here. And again, that's too big for the exact same reason. Now, number 23, that one doesn't have that problem. We have 5 vertices. The biggest degree is 3, so we're good on that. It is supposed to be a simple graph, but that's fine. Our maximum degree is smaller than n minus 1, so we're good. How about even and odd? Are we okay on that account? Yes, okay. So this one should exist, right? And so who wants to be brave and share their screen and draw a picture of it? You have a picture. Okay, so Lucas, here 1 second. Let me allow you to share your screen. 1 moment here. Lucas. Okay, there you are. Okay, and let me stop my video here, and you go right ahead. Very nice. Okay, so A, B, and C are all degree 1, D is degree 2, E is degree 3. Yeah, very nice. Cool. Okay, so let's move on to the next one. Once it loads. All right, the next one is a simple graph with 6 edges and all vertices of degree 3. Okay, so which graph do you think that's going to be? Actually, you don't have to draw a picture. I mean, you can draw a picture of it, but you can answer in the chat. That's a little hint. Not K6, but you're close. 6 edges, not 6 vertices. Not K5. K4, very nice. Yep, it's K4. Nice work, right? Because K4 has 6 edges, right? The square and then the cross in the middle. And then, of course, all the vertices have degree 3 in K4. Okay, how about number 25? Simple graph with 9 edges and all vertices of degree 3. So let's think about this for a minute. The information that's missing that we're going to need to draw this graph is how many vertices there are, right? Now, if we have 9 edges and every vertex has degree 3, how many vertices do there have to be and why? Not 27, no. Much fewer than that. Six. Yeah, that's right. It's 6. How'd you get that, Lucas? What's your thought process there? Okay, so you can make a picture, and that's fine, but you can actually find it from the formulas that we've learned. Can anyone see what the relevant formulas are, how to combine them? Okay, so I'll give you a hint. It has to do with the total degree formula. What's the total? What formula do we know about the total degree? Okay, it's 2 times the number of edges, right? So we can actually find the total degree from problem number 25, right? 9 edges, so what's our total degree? 18, right? And if every vertex has degree 3, then we can figure out how many vertices there are, right? Because it's just 18 divided by 3, which is 6. Very nice, Nathan. Yep, perfect. Okay, so you can do it that way, or you can just try to draw a picture and make the thing work. But it's a little bit nicer if you know how many vertices you have going in. And Lucas, you said you have another picture for us. Is that right? You want to share your screen again? It's a bit uglier. That's fine. No big deal. I've got an ugly picture too. So we'll do both of our ugly pictures. Ooh, boy. But it's supposed to be a simple graph, it said. So you missed that part. Yeah, got to be simple. Okay, so maybe you can try again. Does someone else want to be brave? Or maybe, if you want to describe in English your strategy for how you would approach this problem, that's fine. Okay, so any ideas? Triangular prism. Let me think about that for a minute. Yes, it is a triangular prism. That's exactly right. Yeah, so let me show you here. Here's what I did. Kind of hard to see here. It's a hexagon with a line across and 2 lines down, right? But if you think of that 3-dimensionally, right, there's 2 triangles, one on top of the other, and all of the corresponding corners of the triangle are connected, right? Very nice. Okay, so there's some examples of vertex lists and vocab stuff. And I think that's all I want to do in this section. Any questions on 10.1 before we move on? Okay, so in that case, let's check out 10.2. So 10.2 is the first time we're going to be officially introduced to Leonhard Euler, pronounced Euler. If you say Euler, you'll sound stupid, so don't say Euler, say Euler, right? It's important to pronounce these old white guys' names correctly, right? So let's talk about Euler for a minute. So Euler lived in Königsberg, okay? So in Königsberg, it's a really beautiful little town that had some rivers running through it with bridges over the rivers, much like Portland. But it's a lot smaller and sort of cuter than Portland, with more rivers, okay? So there's a little picture here of Königsberg. There's a little picture of the town. We got an actual map here, right? You can see the rivers coming through. There's the rivers here, and then this one comes down. And there are these different regions of the town, right? So there's region A to the north, B's in the middle, C's to the east, and D's to the south, right? And Euler's problem was that, like any good mathematician, he liked to go out walking, okay? And if you haven't done this yet, you should definitely give it a try, because thinking about math when you're walking is the best way to think about math, bar none. So the next time you are wondering about a math problem, go out and have a walk, right? And it'll help you think about it. Now, Euler was so committed to this idea that he started mathematically analyzing the walks that he would take while he thought about math, as you do. And what he was wondering was, hey, listen, you know, I live in this beautiful town. There's these nice bridges. I would love if I could start at my house and take a walk where I cross all 7 bridges here. You see there's 1, 2, 3, 4, 5, 6, 7 bridges. Can I take a walk where I cross all 7 bridges and end up back at my house? Which was a pretty reasonable question to ask, right? He just wants to see all the sights each day. So, you know, he sees all the neighborhoods and all the pretty stuff, right? But, you know, as always, mathematicians are efficient, AKA lazy, right? And he didn't want to cross any bridge twice. He wants to cross every bridge exactly 1 time, right? And that's the problem of Königsberg. So if we think of this as a graph, right, we've got region A, which is connected to region B by 2 bridges, right? B is connected to C by 1 bridge, A to C by 1 bridge, B to D by 2 bridges, and C to D by 1 bridge. So I could think of this in terms of a graph like this. A connects to B, right? Now the regions of the town have been condensed into single points, and the bridges are the edges, right? So each region of the town is a vertex, each bridge is an edge. So A connects to B by 2 bridges, because up here, A connects to B by these 2 bridges, right? B connects to C by 1 bridge. There's B connecting to C by 1 bridge, and so on and so forth. So you can sort of interpret the connections between the regions by bridges as a graph, right? And in terms of the graph, the following is, the problem becomes, to hit every bridge exactly one time is to say, can we find a route through the graph that starts and ends at some vertex and transverses each edge exactly one time? Because the edges are the bridges, right? So we want to hit each edge exactly one time, but we also want to stop at the same vertex that we started with. Because I don't know which section Euler lived in. It doesn't give a little, maybe his house is like over here somewhere, right? So but the thing is, it doesn't matter which region you started, right? So if Euler lived in, region B, that's not really any different than if he lived in region A in terms of the problem, right? Because if you're trying to find a route through all the bridges, right, and you end back where you started, that's going to make a big loop, right? Because you start at one place, you take all the bridges, go all around, and end back where you started. That whole path that you walked on is going to be a loop, right? And so it doesn't matter which place you started in, because the whole thing makes a loop anyway, right? If you have a circle, right, and you're wondering, oh, hey, I have this circle, right? And I want to walk all the way around the circle and get back to where I started. Well, it doesn't matter if you start here and walk around the circle, or if you start here and walk around the circle. Either way, you're walking around the whole circle. It doesn't make any difference, right? Does everyone understand the argument why it doesn't matter which region Euler's house was in? People happy with that? Okay, cool. So let me redraw the graph here. So we've got A, B, and D. There's A, B, and D, and here's point C over here. So is it possible, we'll just start at A, we'll just start at the top, right? So is it possible to walk down every edge exactly one time and end up where you started? What do you guys think? And you say no. Okay, why not? Poor Euler, his walks were ruined, right? Okay, because C, you have to go there and back. It would have to have an even number of edges. Ah, okay. So in order to get there and back, you have to have an even number of edges. Oh, let me play devil's advocate. That one works, right? That one has a circuit where you go down each path exactly once, right? But it has an odd number of edges. Did I misunderstand your argument, or have I successfully argued against you? Oh, okay. 3 edges are emitted from C. Okay, I got you. So you mean the degree of C is odd, I guess, right? Yeah, okay, got it. All right. So C has an odd degree. Let's see, who else has an odd degree? So does A and D and B. Actually, they all have an odd degree. Okay. So all of the vertices have an odd degree. And okay, so let me reinterpret your argument there. You said you have to go there and back, so it would have to have an even number of edges. So I think what you meant by that is to go there and back, you would have to have even degree at those vertices. Is that what you meant? Or are you trying to shoot for something about? It's about even and odd, right? It's about even and odd numbers. But were you trying to shoot for the degree being even or odd, or the number of edges being even or odd, or both? The argument only works in combination with the even parallel loops. Sure. So if C wasn't there at all, if we just forgot about all this, right, then Euler would have a path, right? You could just go down on the left, down to D, then back up on the right, back up to A. and that would work fine. Now, if we had gotten rid of C, right, then we wouldn't have an odd number of edges connected to C. Well, the number of edges connected is just the degree. So we wouldn't have an odd degree for C anymore. But notice we also wouldn't have an odd degree for A, B, or D anymore either, because we're taking one away from one, road, one edge away from each of these three. So now the degree of A is 2, B is 4, and D is 2 for our degree counts, right? So do you think that whether or not an Euler circuit exists is connected to degree count or edge count? Edge count. Okay, so you're sticking with edge count. Okay, sure. So how would you describe it then, right? There can't be. Yeah. So how? Yeah, you tell me. How would you describe that exactly? Or someone else want to jump in? Someone disagree? Someone think it has to do with degree count instead of edge count? What do you guys think? Okay, so how about this? Do people agree that there's not a path that goes through? Does anyone think there is a path that goes through? I mean, of course, if we get rid of C and all of its adjacent edges, then it works. But what about if we have C on there? Okay, let me help a little bit. How about this? Obviously, there's a circuit that works here with X and Y. Right? Maybe it has to do with the difference in degrees. Yeah, that could be. I'm not going to give you the answer. I'm going to let you guys figure it out, but I'm going to help you along. Okay. So obviously there's a path from X to Y and back to X. And so this one works. This one has an Euler circuit. What if I put in another edge from X to Y? Does it work now? Remember, you have to end where you started, right? So no, it doesn't work. So if we go from X to Y, and then either way we go back to X doesn't matter, right? If we go back to X on this one, we still have this one to do, and that'll leave us at a spot that's not where we started. Or if we go X to Y and then take this one, well, then we have the straight one left to do, and that won't work either because that'll land us at Y, which is not where we started. So this situation doesn't work, right? How do I fix it so that it works again? Add another edge. Now it works, right? So I can do the outer ones, go X to Y and then back to X. And I'll do the inner ones, X to Y and then back to X, right? So it seems like, and if I put on a fifth one, now does it work? No again, right? Because now I'll do those 4 right? I'll do x to y to x to y to x, and then I still have that fifth one, which then screws it up. Well, edges don't have to be a multiple of 4, because what can I do now to fix it? Add another degree and add another edge, right? Here, I'll put it up here. Just add another one, right? Now I can go there and back on the top two, there and back on the next two, then there and back on the last two, right? Which is not a multiple of 4. So there's 6 edges, which is not a multiple of 4. You want the total degree to be a multiple of 4. Okay, so in that case, let's see if I can come out with one that doesn't work. Here, let's do K3. Pardon me, K4. This has a total number of degree of 12, which is a multiple of 4, but I claim that there is not an Euler circuit in this graph, K4. What do you guys think? So let's start at A, right? Can I hit every edge and get back to where I started? No. Okay, why not? The diagonals don't have parallels. Okay, that's a way of putting it. So, so it seems like, were you trying to walk around the outside first, David? Were you trying to go A, B, D, C, A, like around this, and then do the diagonals? Or what was your strategy like to try to find a path here? Or if someone else wants to jump in, you can go for it. So let me ask one more time. Why doesn't this have an Euler circuit? I agree with you that it doesn't. Okay, Lucas, you're saying the degree of every vertex needs to be even, because otherwise you get stuck on the vertex because you'd go in, but you wouldn't be able to go out. Perfect. That's exactly the right idea. Think of it this way. You have some vertex, okay? And you have some of the graph over here, some of G over here, and some other stuff of G over on the other side. But we're just going to think about one vertex, okay? Now, if that vertex has degree 2, okay, well, then there's some options here, right? We could have this situation where both of the degrees go to one side of the graph. Could have another option where the degree goes to both sides of the graph. Okay, so what we could do is we could be over here. We're in part of the graph. We jump out to our vertex, and we come back into this part of the graph, and we've successfully entered and left this vertex. So we came in and we went out, right? So, or with arrows, we'd sort of think of it like this, right? These aren't actually directed graphs. I'm just thinking about walking down an undirected graph, right? Or in this situation, I could, come in like this, or I go in from one side and out on the other. But what I can't have is I can't have this. right? Because if I was to go in here and out here, well, that means I have to be going in on the last one, and now there's no way out that I haven't already done before, right? Well, what if could I arrange it a different way? What if I said, instead of this one being in and out, what if I said, this one is in and this one is out? Well, I'm gonna have the same problem because I'll come in on the top one. So that's not gonna work. What if I come in on one and out on the other here? Well, for this one, I would have to be coming in to come into it, right? So basically the idea is, well, one edge is the way to get in, the other edge is the way to get out, and if there's a third one, then you have to be coming in on that edge because you've already left it for this vertex before. Maybe you come around, you've gone around the long way back to the other side. There's another connection down here maybe. You've come back in, and now there's no way out again because you've already taken that road, right? That bridge. What do you guys think? Does that argument make sense? Questions? Okay, so in order for an Euler path to exist, an Euler path requires, an Euler circuit, pardon me. Helps to use the right vocabulary. An Euler circuit requires every degree, vertex degree, to be even. Okay. I think what I should do now is talk about the distinction between a circuit and a path, but does anyone have any questions here? We good on that? Okay, so let's do some vocab. I'm just gonna show it to you and talk through it rather than spending all this time writing. There we go. Okay, so here goes. Almost, if I can get this thing to stop being stupid. There we are. Okay, great. So G is a graph. V and W are vertices in the graph. A walk from V to W is a finite alternating sequence of adjacent vertices and edges. So a walk has the form V0, whatever vertex you're starting at. Then you take an edge, which takes you to another vertex, you take another edge, which takes you to another vertex, and so forth, till eventually you're at some vertex, take your last edge to your stopping point. Okay, the V's are the vertices, the E's are edges, and for all of the I's, VI are the endpoints of E. You can also walk from V to V by not going anywhere. So if I want to go to my house, I can do that by sitting here in this chair, which currently resides at my house. And that counts as me going to my house, which is kind of a stupid way of talking about it, but there you go. It's stupid because it's trivial, and trivia is stupid, which is why I hate trivia night, because I never win, because it's stupid, right? So trivial walk from V to V means you didn't actually go anywhere. You just stayed where you started, okay? Or a walk could be non-trivial, which means you actually go out on the graph, follow some edges, get to some vertices, and end up possibly somewhere else, possibly where you started, depends on the walk, right? Okay. So a walk is just going through the graph, no restrictions. What we're going to do is we're going to start to add restrictions on our walks, which is going to give us these other vocab terms. Okay, so what's a trail? A trail is a walk that doesn't contain a repeated edge. Okay, so you can think of a trail sort of like, in the forest, right? If you go hiking on a trail, usually you don't walk down the same stretch of trail twice, right? If you go on a hike, usually you go, you sort of walk, you don't want to hike down the same place twice because you've already seen it, right? Okay. A path is a trail that doesn't have a repeated vertex. Okay, so let's do a trail that's not a path and a trail that is a path. So how about in this example here? Can someone give me an example of a trail in this graph that is not a path? And finally, a trail that is a path. So first of all, what's a trail that's not a path? Someone tell me one. Or just any trail at all. We'll just say any trail at all. Then we'll decide if it's a path or not. How about that? Someone just give me a trail, which is a walk that does not contain a repeated edge. So someone give me a trail in this graph. Doesn't have to be long. Okay. F1, F3, F5, F6, F7, F2. Okay, well, that's definitely a trail because you didn't repeat any. Those edges are all different. But for any walk or trail or path or any of these guys, you do want to list the vertices out as well. So for your path, I think that, or for your trail rather, sorry, it would actually be U1, F1, U2, F3, U3, F5, U4, F6, U4, F7, and then U2, F2, U5. Okay, let me put some spaces in here. I think that'll help. I just put some spaces to make it a little bit easier. You could space it out differently if you wanted to, but I think that kind of is a nice way of doing it. You got the vertex and then where you go, then a vertex and then where you go, right? So David, that absolutely is a trail. You just wanted to intersperse the vertex names in there. So, okay, so is that trail a path or not? Remember, a path does not contain a repeated vertex. So is that trail a path? Not a path. Good. Which vertex has been repeated? U2, good. And U4 as well. Those have both been repeated. Cool. So can someone give me a trail that is a path? Doesn't have to be long. It also doesn't have to start at U1 necessarily. Okay, U1, F1, U2, F2, U5. So we go boom, boom. Good. That is a trail, which is also a path because there are no repeated edges and no repeated vertices. Beautiful. Nice work, Natasha. How about another one? Someone give me another path. Okay, U3, F5, let me point with this thing, it's better. U3, F5, U4, F7, U2. So I go boom, boom, that is a path. Excellent. All right, moving right along. A closed walk is a walk that starts and ends at the same vertex. Okay, so a closed walk would be, if I went U2 to U3 to U4, did the loop, and then came back to U2, right? That would be a closed path. Or I could go from U5 to U2 and back. That's also a closed walk, right? So a closed walk just means you start and stop at the same point. And that's right, David, a path can never have a loop on it, because if you have a loop, then, well, you can never walk down the loop, right? If I go U2, F3, U3, F5, U4, and then stop, that's fine. That's fine for a path. So the graph can have a loop in it and still have a path, but if you have a path, you can't actually walk down the loop, right? Because that will start you and stop you at the same point, which is not allowed for a path. Does that make sense, David? The graph can have a loop, but the path can't. Yep, awesome, good. Okay, cool. So that's a closed walk. A circuit is a closed walk that contains at least one edge and does not contain a repeated edge. So really, a circuit rather, is like a closed trail, right? It's just a closed, non-trivial trail, contains at least one edge, right? So a closed, non-trivial trail is called a circuit, right? Or you could call it a closed trail, that's fine. But the general term is circuit, right? And then a simple circuit is like a closed path, right? It's a circuit that doesn't have any other repeated vertex except the first and last, right? So a circuit is like a closed trail. A simple circuit is like a closed path, right? And a simple circuit is, pardon me, just a regular circuit contains at least one edge and doesn't contain a repeated edge, right? That's what we're shooting for with an Euler circuit. So what's the difference between a circuit and an Euler circuit? The kind of walk that we were talking about at the very beginning. Are they the same? Is there a difference? So what's the difference between a circuit and an Euler circuit that we were doing before with the bridges? So how about this? A circuit is a closed walk that does not contain a repeated edge. In other words, it's a closed trail, right? So can someone give me a closed trail, AKA a circuit, from this graph? Let's do that, right? So someone give me a circuit in this graph. Okay, U2, F3, U3, F4, right? I start at U2, I take F3 across and F4 back, so I don't have repeated edges, and I start and stop at the same place. That's exactly right, Sean. Beautiful. Is that an Euler circuit? Good. It's not, because it doesn't touch every edge. The whole idea of the Euler circuit is that he wanted to walk down every bridge, every edge, right? And here we only did 2 of them, and there's a bunch we didn't do. So in this particular case, it's not an Euler circuit. So the difference here between a circuit and an Euler circuit, a circuit has at least one edge, an Euler circuit has every edge, right? Okay, a simple circuit is a circuit, so no repeated edges, that also doesn't have any repeated vertices. So can someone give me an example of a simple circuit in this graph? It doesn't have any repeated vertices except for the first and last one. Obviously that has to be repeated if it's closed, right? But other than that, it doesn't have any vertices repeated. So can someone give me a simple circuit in this graph? Yeah, that would be a simple circuit as well, the same one, right? Because you're going U2, taking F3 to get there, taking F4 to get back, right? And you haven't repeated any edges and you haven't repeated any vertices except for U2, which is where we started and stopped, so no big deal. Another simple circuit would be U2 over to U3, then to U4, and back to U2, right? So if we made like a little triangle here, that would also be a simple circuit. Yeah. We could also take, F4 across and do that same triangle, and that would also be a simple circuit. Questions? Okay, so let me ask you this. We have a walk, a trail, and a path. A closed walk, a closed trail, which is called a circuit, and a closed path, which is called a simple circuit. Now we have a circuit that contains every edge, called an Euler circuit. How about a simple circuit that contains every vertex? Does anyone know what that's called? It's our last little vocab, Hamiltonian, right? After Sir William Hamilton back in the 1800s, right? So Euler, he was an Austrian guy in the late 1700s. Hamilton was an Irish guy in the 1800s. So there you go. So great. Maybe we should do, let's go over the table real quick, and then I think we'll call it for today. So here's a little table of what all the things mean. Okay, so a walk, you're allowed to do whatever you want, right? You don't have to contain anything, everything's allowed. A trail has no repeated edge, and that's it. A path has no repeated edges or vertices, okay? A closed walk has everything allowed. You don't have to have an edge, right? But you do have to start where you stopped, right? There's a yes. Start and end at the same point, yes, right? Circuit, you can't have a repeated edge, and you have to start and stop at the same point. Simple circuit, you can't have a repeated edge, and you can't have a repeated vertex other than the first one, right? And you have to start and stop at the same point. A couple more on here, if they finished this out. An Euler circuit would be a circuit where every edge is included. A Hamiltonian is a simple circuit with every vertex included. Also VV important in physics. What, the Hamiltonian? Or Hamilton, yes. Yes, Hamilton is important in physics. The Hamiltonian, not to my knowledge, although I'm sure it probably is somewhere. I quit physics and transferred over into math instead because it was too hard. So yeah, I'm sure the Hamiltonian's involved somewhere in physics as well. But yeah, there's other functions and concepts in physics from Hamilton and Euler as well, for that matter. So there you go. Okay, cool. So we've got 1 minute left. Let me stop it there. Does anyone have any questions for me before we go? Okay, well, sounds good then. Have a great day, everybody, and I will see you on Wednesday. See you later, guys.